Every moment you've been alive, something impossible has been happening around you. While you blink, while you breathe, while you exist, the fabric of reality itself stretches by millions upon millions of miles. The cosmos isn't just getting bigger missions, it's manufacturing space from absolutely nothing, second by second, defying everything your mind thinks it knows about how things work. But wait, here's where your brain completely short-circuits. This expansion isn't happening into anything. No giant container exists. No cosmic warehouse stands ready. No boundary separates inside from outside. What we're about to explore will shatter every assumption you have about existence itself. Get ready to discover why the universe operates like a magician pulling space from an empty hat. Witness the invisible destroyer ripping reality apart at the seams, and learn why questioning what surrounds our cosmos is identical to asking what direction lies beyond the North Pole. Like and subscribe because this journey will change how you see everything forever. Your everyday experience teaches you lies about expansion. When you inflate a party balloon in your home, the rubber pushes outward against surrounding air. The balloon grows because your room provides territory for that growth. This process makes complete sense. Objects expand into available areas. Everything bigger requires somewhere to become bigger. Your mind automatically applies this same logic to cosmic expansion. When astrophysicists explain that our cosmos grows larger, you envision that familiar balloon scenario. You picture space stretching outward into some colossal chamber, some infinite emptiness patiently waiting to be occupied. You assume a border must exist where our reality concludes, and something different commences. This assumption feels completely reasonable. It appears obvious. Unfortunately, physics demolishes these comfortable beliefs without mercy. Cosmic expansion operates nothing like your balloon example. When spatial dimensions expand, they don't invade anything. No cosmic chamber exists, no container waits, no exterior realm stands by. The cosmos manufactures the fundamental concept of space as it develops. Consider this analogy. Try drawing a circle larger than your paper allows, rather than finding bigger paper. Imagine the paper itself growing to accommodate your circle. This seems impossible because everything in our world expands into something else. Vegetation grows into air. Metropolitan areas expand into rural regions. Ice spreads across water surfaces. Always, territory exists for expansion to occupy. Always, boundaries separate expanding objects from their expansion destinations. But what happens when you simultaneously become both the paper and the drawing? Scientists uncovered this reality-breaking truth through distant galaxy observations. Edwin Hubble discovered that remote galaxies race away from us faster than nearby ones. Initially, this observation suggests we occupy some cosmic explosion's center, sitting motionless while everything else flies outward into vacant territory. The actual truth proves far more bizarre. Space itself stretches. Galaxies aren't traveling through spatial dimensions. The dimensions between them grow larger. Visualize dots marked on a deflating balloon but reversed. As the balloon inflates, dots separate without moving across the surface. The surface itself expands. Each dot observes every other dot receding. No dot holds special status. No dot occupies the center. Now substitute that balloon surface with the three spatial dimensions surrounding you. Our cosmos doesn't expand into anything because no anything exists for expansion to occupy. Reality creates the stage where expansion performs. This concept destroys intuition so thoroughly that even genius scientists battled it for generations. Albert Einstein initially dismissed this possibility. Yet this seemingly impossible expansion accelerates right now beyond imagination. How do we confirm this bizarre process actually occurs? The solution involves observing light itself getting tortured by expanding dimensions. When distant galaxies launch light beams toward Earth, that radiation begins its voyage with specific wavelengths. Blue light, red light, infrared radiation, each wavelength carries unique signatures like cosmic fingerprints. But during light's journey through expanding space, something remarkable occurs. The spatial dimensions that light traverses grow larger throughout its voyage. Picture walking across a moving walkway that slowly stretches while you walk. Your steps maintain consistent size, but the ground beneath continuously grows longer. By journey's end, you've traveled much farther than your steps should have carried you. Light experiences similar effects, except rather than traveling farther, its wavelength gets stretched. Blue radiation from remote galaxies reaches our telescopes as red radiation, not because galaxies moved away like speeding ambulances altering siren pitch. Light reddens because spatial dimensions expanded during radiation's billion-year voyage. Each light wave gets pulled longer as cosmic fabric grows beneath it. This phenomenon, called cosmological redshift, proves that spatial dimensions grow independently of contained objects. Here's the number that will completely rewire your brain. Radiation from the most distant observable galaxies has stretched to nearly 40 times its original wavelength. The spatial dimensions that light traversed expanded so dramatically that intense ultraviolet radiation now reaches us as faint infrared heat. 40 times longer wavelengths means our cosmos expanded by a factor of 40 during that light's journey. Contemplate this reality. The galaxy that transmitted this ancient radiation appears tiny and dim in our most powerful telescopes. But when that light initially departed the galaxy, our cosmos measured 40 times smaller than today. That galaxy existed much closer to where our Milky Way would eventually develop. Spatial dimensions didn't just grow slightly, they underwent massive, relentless expansion. Here's what makes this even more mind-bending. This stretching isn't occurring somewhere distant. It's happening everywhere. Right now, the spatial dimensions in your current location attempt to expand. The space separating your eyes from this screen wants to grow larger. The only reason you don't detect this expansion is that electromagnetic forces between atoms far exceed the expansion rate. Only across vast cosmic distances does this expansion become noticeable. The spatial dimensions between galaxies contain no atomic forces to maintain cohesion, so they expand freely, transporting those galaxies apart like raisins in rising bread dough. The raisins don't move through the dough expands and carries them apart. This explains why asking what does the cosmos expand into completely collapses as a meaningful question. You're demanding to know what the dough stretches into, but you exist as part of that very dough. Yet if spatial dimensions stretch everywhere, exactly how far can human vision actually penetrate? We inhabit the ultimate celestial prison, and its walls consist of time itself. Every evening when you venture outside and gaze upward at stellar formations, you feel like you're witnessing the cosmos, the complete thing, all of reality sprawled above you in that dark expanse. But here's the truth that will revolutionize how you comprehend existence. You're observing less than 4% of what actually surrounds you. You remain trapped within an invisible sphere. This sphere possesses a radius of approximately 46 billion light-years. Beyond this barrier lies additional cosmos, billions more galactic collections, trillions more stellar bodies, perhaps even alternate versions of yourself absorbing these very concepts. But you will never witness any of it. Not with any telescope humanity could ever construct. Not with any technology that could ever emerge. The confinement isn't constructed from walls or blockades. It's manufactured from light's finite velocity combined with our cosmos's finite age. Electromagnetic radiation requires duration to traverse distances. When you observe our solar star, you witness it as it appeared 8 minutes previously. When you examine the nearest stellar system, Alpha Centauri, you observe it as it existed 4 years ago. Gaze at the Andromeda galactic cluster, and you're perceiving 2.5 million years into history. The farther you peer into spatial dimensions, the deeper you delve into the past. Here's where the confinement seals around you. Our cosmos measures 13.8 billion years old. This means the most ancient radiation that could possibly reach you has traveled for 13.8 billion years. Any galactic formation farther than 13.8 billion years distant might as well not exist from your viewpoint. Its electromagnetic radiation simply hasn't possessed sufficient duration to arrive yet. But hold on, later the confinement becomes even more restrictive. Remember that spatial dimensions have expanded this entire duration. That remote galactic formation existed much closer to us when it discharged the radiation we detect today. By the moment its ancient light reaches our telescopes, expansion has transported that galaxy far beyond the 13.8 billion light-year marker. Today, that galaxy sits approximately 46 billion light-years away from us. This constructs your celestial prison cell. Everything beyond 46 billion light-years from Earth exists in what researchers term the unobservable cosmos. You cannot witness it. You cannot detect it. You cannot prove it exists. Yet logic and mathematics inform us it must be there. Consider yourself standing in dense fog that restricts your vision to 100 yards in any direction. You can see a circular area around you, but you know the world continues beyond that fog. The observable cosmos represents your fog-limited circle, while the actual cosmos stretches infinitely in all directions. Here's the number that should simultaneously terrify and amaze you. If our cosmos proves infinite, then your observable bubble contains 0% of what actually exists. 0%. But what lies beyond our celestial prison walls? The most ancient radiation in existence screams toward you right now at 600 million miles per hour, and it carries a message from the moment reality commenced. This electromagnetic radiation has traveled longer than Earth has existed, longer than our solar system formed, longer than our galaxy assumed its current configuration. This radiation began its voyage when the cosmos measured only 380,000 years old, back when the universe consisted of seething plasma, so intensely hot that atoms couldn't even materialize. We call this ancient radiation the cosmic microwave background, and it's everywhere. Switch on an old television between channels, and approximately 1% of that static originates from this primordial light. You're literally witnessing the afterglow of creation flickering across your screen. This radiation fills every cubic inch of spatial dimensions. It arrives from every direction simultaneously. It represents the oldest phenomenon human eyes can detect. But here's what makes this discovery so profound. This radiation represents the edge of everything we can observe. Before that moment, 380,000 years after the Big Bang, our cosmos was opaque. Picture attempting to see through the surface of our sun. The early universe resembled that everywhere mites a thick fog of plasma that blocked all electromagnetic radiation. No photon could travel more than a few inches before colliding with charged particles and getting absorbed. Then something miraculous occurred. The expanding cosmos cooled sufficiently for protons and electrons to combine into the first hydrogen atoms. Suddenly, the celestial fog lifted. Reality became transparent. Electromagnetic radiation could finally travel freely across spatial dimensions. The first photons that escaped this cosmic clearing are the ones reaching your eyes today as the microwave background. This moment, called recombination, created the ultimate horizon. You cannot see past it, ever. Any events that occurred in those first 380,000 years remain forever hidden. It's like attempting to see through a brick wall that surrounds the entire early cosmos. The cosmic microwave background is that wall, and it represents the absolute limit of observation. Here's the mind-bending aspect. This horizon moves every second that passes. Electromagnetic radiation that has traveled for 13.8 billion years plus 1 second reaches us. The observable cosmos grows by 1 light second every second. That's about 186,000 miles of new spatial dimensions coming into view. Every day we can see about 16 billion miles farther into the universe. But expansion complicates this growth. While our observable horizon expands, the actual distance to the source of that ancient radiation keeps increasing due to cosmic expansion. The galactic formation that emitted a photon 13 billion years ago now sits about 30 billion light-years away from us. We witness where it was, not where it currently resides. This creates a bizarre situation. We're constantly witnessing new regions of spatial dimensions, but the sources of that radiation are constantly moving farther away from us. It's like watching a movie of someone walking away from you while the screen gets bigger. The cosmic microwave background shows us the cosmos when it was smoother than a perfectly polished mirror, with only tiny temperature variations of a few millionths of a degree. These minute fluctuations represent the seeds that would eventually grow into every galactic formation, every stellar cluster, every planet you see today. You're witnessing the blueprint of everything that exists. Those microscopic temperature differences would eventually transform into everything that exists. But what occurs when we push beyond even this ancient horizon, past the edge of everything your vision can penetrate, lies more of exactly what your vision already captures. This sounds tedious, but it's actually the most disturbing possibility in cosmology. If you could somehow teleport 47 billion light-years away beyond your observable boundary, you'd discover yourself in a region that appears remarkably similar to here. Additional galactic formations, additional stellar bodies, additional planets, possibly additional life forms. The cosmos appears to be homogeneous on the largest scales. Homogeneous means uniform, identical everywhere, like perfectly mixed cake batter where every spoonful contains identical ingredients in identical proportions. Our observations of the cosmic microwave background suggest that reality possesses this property. The tiny temperature variations we detect are smooth and consistent across the entire celestial dome. This smoothness reveals something profound about what lies beyond our sight. If the observable cosmos contains roughly 2 trillion galactic formations, then a region of identical size just beyond our horizon should contain roughly 2 trillion galactic formations as well. Another region beyond that should contain another 2 trillion. The pattern continues forever, or at least much farther than we can comprehend. But here's where this becomes psychologically disturbing. If spatial dimensions are truly infinite and homogeneous, then every possible arrangement of matter within any given volume must repeat somewhere. This isn't mystical thinking. It's a mathematical necessity. With infinite space and finite ways to arrange a finite number of particles, repetition becomes inevitable. Picture having a deck of cards and shuffling it infinitely many times. Eventually, you must get identical arrangements twice. Reality works similarly, but with atoms instead of cards. This means other versions of you are reading these words right now, not metaphorically, mice literally. In regions of spatial dimensions so distant that their electromagnetic radiation will never reach us, quantum mechanics has arranged matter in every possible way, including ways identical to your current configuration. There are versions of you where you decided to stop reading this sentence, versions where you never existed, versions where the entire history of Earth played out differently. The mathematics suggest these copies exist at distances of roughly 10 to the power of 10 to the power of 115 meters away. That's a number so enormous that if you wrote it out, the line of digits would stretch across more spatial dimensions than exists in our observable cosmos. Yet if space proves infinite, these distances remain finite. Somewhere out there, another version of you is having this same realization about yet another version of you even farther away. The chain continues endlessly, creating an infinite hierarchy of identical moments happening simultaneously across incomprehensible distances. But wait, this assumes the cosmos beyond our horizon resembles the cosmos within it. What if it doesn't? Recent observations hint that our local region might be unusual. We seem to exist in a cosmic void, a region with lower than average galactic density. If this proves true, then traveling beyond our observable horizon might reveal denser regions of spatial dimensions packed with additional galactic formations, additional black holes, additional activity. Or it might reveal regions that are nearly empty. Some theoretical models suggest that cosmic inflation-ness, the rapid expansion in reality's first fraction of a second-ness, could have created regions with vastly different properties, different physical constants, different particle types, different laws of physics entirely. These pocket universes might exist just beyond what we can observe, operating under rules that would render our physics textbooks worthless. Imagine regions where gravity works in reverse, where time flows backward, where consciousness manifests in ways we cannot comprehend. These alien domains might exist mere inches beyond our observable boundary, yet remain forever hidden from our detection. The cosmos might contain infinite laboratories where different versions of reality play out their own unique experiments. However, there's an even more fundamental question lurking beneath all this speculation. What if the cosmos isn't infinite at all? An infinite cosmos that expands presents one of the most beautiful paradoxes in physics. How do you make infinity larger? Mathematics tells us this should be impossible. Infinity plus anything still equals infinity. Infinity multiplied by 2 still equals infinity. You cannot add to something that already contains everything. Yet our observations clearly show that spatial dimensions expand everywhere. Even if reality extends infinitely in all directions, the solution comes from understanding what expansion really means. When we say the cosmos expands, we don't mean it grows larger in the sense of becoming more infinite. We mean the scale of space itself increases. Consider this analogy. Picture an infinite piece of graph paper where each square measures 1 inch wide. Now visualize stretching that paper so each square becomes 2 inches wide. The paper remains infinite. It still possesses infinitely many squares, but the distance between any two marked points has doubled. This is exactly what happens during cosmic expansion. Reality doesn't become more infinite. The scale factor of spatial dimensions increases, making all distances grow proportionally. A galactic formation that's 100 million light-years away today was 50 million light-years away when the cosmos was half its current size. But this creates a disturbing implication. If reality is infinite now, it was also infinite at the moment of the Big Bang. This means the Big Bang wasn't an explosion of matter and energy from a single point into empty spatial dimensions. It was the simultaneous expansion of infinite space filled with infinite energy at every location. Wrap your mind around this concept. The Big Bang occurred everywhere at once across infinite spatial dimensions. There was no center, no edge, no outside maquets, just infinite space suddenly beginning to expand and cool. Every point in reality can claim to be the center of expansion because expansion appears identical from every location. This infinite perspective solves several cosmic mysteries while creating new ones. It explains why reality appears identical in all directions from our vantage point. In infinite homogeneous space, every location is equivalent. You're not special because you exist at the center of expansion. Every observer in every galactic formation sees themselves at the center of their own observable bubble. But this also means that the total energy content of reality is infinite. The total number of particles is infinite. The total number of black holes, stellar formations, and potentially conscious beings is infinite. We're not just dealing with large numbers, we're confronting actual mathematical infinity made manifest in physical reality. This transforms every question about cosmic origins. Instead of asking how something came from nothing, we must ask how infinite something reorganized itself. Instead of questioning what caused the Big Bang, we must understand what triggered infinite space to begin expanding simultaneously everywhere. The cosmos doesn't just contain everything we can imagine, it contains everything that can possibly exist, repeated infinite times across infinite distances. It also explains why we don't witness evidence of a boundary or a center. No boundary or center exists to witness, but it raises a haunting question. If reality contains infinite matter and energy, how do we avoid infinite density? The answer lies in recognizing that density equals matter divided by volume. Even if both matter and volume are infinite, their ratio can still be finite. Reality can contain infinite stuff spread across infinite spatial dimensions while maintaining a specific average density of about 5 hydrogen atoms per cubic meter. Here's where the paradox becomes personal. In an infinite cosmos, every possible event that can occur will occur infinitely many times. Not just the repetitions of you we discussed earlier. Every possible version of every possible story plays out somewhere in the vast expanse. Every tragedy, every triumph, every moment of beauty, and every act of cruelty unfolds across infinite stages. If this troubles you, consider the alternative. A finite cosmos raises equally disturbing questions. What lies beyond its boundary? How can spatial dimensions themselves have an edge? What happens if you try to travel past that edge? These questions led many researchers to prefer infinite models despite their conceptual difficulties. Recent measurements of the cosmic microwave background suggest our cosmos is either infinite or so enormous that any curvature is undetectable. The simplest interpretation is that spatial dimensions extend infinitely in all directions. This means the expansion you observe isn't creating new space in the sense of adding rooms to a house. It's stretching the infinite fabric that already exists. But if spatial dimensions aren't being created, what exactly drives this relentless stretching? Reality manufactures new space from pure nothingness, at a rate that would make every factory on Earth weep with envy. Every second, the volume of observable space increases by roughly 10 to the power of 78 cubic meters. That's a number so massive that if you tried to count that high, one number per second, you'd need more time than the cosmos has existed, multiplied by itself billions of times. All this new space emerges from quantum vacuum. Quantum vacuum isn't the empty void you might picture. It's a seething foam of virtual particles popping into existence and annihilating each other in timeframes shorter than the smallest measurable instant. This process, called quantum fluctuation, fills every point in spatial dimensions with energy. Even in the most perfect vacuum, this quantum activity continues. Here's the mind-bending aspect. This vacuum energy has gravitational effects. But unlike matter, which pulls things together, vacuum energy creates repulsive gravity. It pushes spatial dimensions apart. The more space you have, the more vacuum energy you get. The more vacuum energy you get, the more space expands. The more space expands, the more room exists for new vacuum energy. This creates a runaway process called inflation. During reality's first tiny fraction of a second, this process ran wild. Spatial dimensions expanded faster than electromagnetic radiation could travel, not because anything moved faster than light, but because space itself grew faster than light could cross it. Picture attempting to walk across a treadmill that accelerates faster than you can run. In less than a trillionth of a trillionth of a trillionth of a trillionth of a second, a region smaller than a proton expanded to roughly the size of a basketball. This sounds like science fiction, but quantum mechanics demands it. The uncertainty principle tells us that energy can be borrowed from the vacuum as long as it's paid back quickly enough. During inflation, reality borrowed massive amounts of energy to create new spatial dimensions, then used the expansion itself to pay back the debt. It's like taking out a loan to buy a money printing machine, then using the printed money to pay off the loan. The process worked so effectively that it overshot. Inflation should have stopped after creating enough space to solve certain cosmological problems. Instead, it kept going, creating far more spatial dimensions than necessary. Our entire observable cosmos represents just one tiny patch of the vastly larger inflated region. Consider blowing up a balloon to the size of Earth, then examining just one patch the size of a pinhead. That pinhead represents our observable cosmos compared to the region inflation created. But here's what makes this truly bizarre. The process continues today. Current expansion isn't inflation, but it operates on similar principles. Dark energy, which comprises roughly 68% of everything, behaves exactly like vacuum energy. It fills spatial dimensions uniformly and creates repulsive gravity that accelerates expansion. As reality grows, additional dark energy appears to fill the new space. This violates every intuition you have about energy conservation. Energy cannot be created or destroyed. Yet expansion seems to create new dark energy continuously. The resolution lies in understanding that gravitational potential energy is negative. As spatial dimensions expand, matter becomes more spread out, reducing gravitational binding energy. This negative energy balances the positive energy of newly created dark energy. Reality maintains perfect energy balance while creating infinite new space. This process will continue forever, or at least for longer than human minds can comprehend. Each moment brings new spatial dimensions, new dark energy, and accelerated expansion. The cosmos grows not because it needs room to expand into, but because expansion creates its own room. Yet all this cosmic creativity pales compared to what happened in that first fraction of a second. What evidence proves this impossible-sounding story actually occurred? Hidden in the static of old television sets lies proof of the most violent event in cosmic history. In 1964, two radio astronomers at Bell Labs were trying to eliminate annoying background noise from their antenna. No matter what they did, a persistent hiss remained in their data. They cleaned bird droppings off the equipment. They recalibrated their instruments. They pointed the antenna in different directions. The noise never disappeared. That noise was the echo of creation itself. What Arno Penzias and Robert Wilson had accidentally discovered was the cosmic microwave background, the afterglow of the Big Bang, stretched and cooled by 13.8 billion years of expansion. This discovery earned them the Nobel Prize and provided the most direct evidence we have for the expanding cosmos model. But this electromagnetic radiation carries more than just proof of expansion. It contains the blueprint of everything that exists today. Those tiny temperature variations, smaller than a few millionths of a degree, represent the quantum fluctuations that would eventually grow into every galactic formation, every stellar cluster, every planet orbiting every sun across infinite space. You're witnessing the moment when quantum uncertainty became cosmic structure, the instant when probability waves collapsed into the reality you inhabit. Every atom in your body, every breath you take, every thought you think might, all of it traces back to those primordial fluctuations captured in that ancient radiation still washing over you from every direction in space. The cosmos didn't just create space and time, it created the very possibility of existence itself. Here's why this radiation proves so crucial. It carries the signature of cosmic expansion, literally imprinted in its wavelength. When this electromagnetic energy first escaped the early cosmos, it was brilliant, visible light with a temperature of about 3,000 degrees. But as spatial dimensions expanded, the wavelength stretched along with it. What started as intense visible photons became infrared radiation, then microwave radiation, then radio waves. Today, this ancient light reaches us at a temperature of just 2.7 degrees above absolute zero. The cosmic microwave background is perfectly uniform to within a few parts in 100,000. This uniformity proves the early cosmos was incredibly smooth, just as inflation theory predicts. Without inflation's rapid expansion to smooth out irregularities, we should see dramatic temperature variations across the sky. Instead, we witness almost perfect uniformity. But those tiny temperature variations that do exist tell an even more remarkable story. They represent the quantum fluctuations that inflation stretched from subatomic scales to cosmic scales. These microscopic ripples in the early cosmos eventually became the seeds that grew into galactic formations, stellar bodies, and planets. You exist because of quantum uncertainty amplified by cosmic expansion. Advanced satellites like the Cosmic Background Explorer and Planck have mapped these temperature variations with exquisite precision. The patterns they reveal match inflation theory predictions so precisely that cosmologists can measure fundamental properties of reality from this ancient electromagnetic energy. We can determine that spatial dimensions are geometrically flat or within measurement error. We can calculate that ordinary matter comprises only about 5% of the total cosmos. We can measure the expansion rate and age of reality to remarkable accuracy, all from studying static. But the cosmic microwave background reveals something even more profound about expansion. The electromagnetic radiation shows us that the observable cosmos today was once compressed into a region roughly the size of a beach ball. Everything you can witness in the night sky, hours of galactic formation visible to our most powerful telescopes. This compression wasn't like stuffing matter into a small container. Spatial dimensions themselves were compressed. The beach ball didn't contain the early cosmos. The beach ball was the early cosmos. No outside existed, no surrounding space, just that compressed region of space-time beginning its expansion into the reality we inhabit today. This realization leads to a disturbing question. If all the spatial dimensions we can observe were once compressed into such a tiny volume, what was providing the energy to drive such dramatic expansion? The answer involves a force that comprises more than 2/3 of everything, yet remains completely invisible. How do you detect something that hides in plain sight? In 1998, two teams of researchers set out to measure how much cosmic expansion was slowing down, and instead discovered that expansion is speeding up. This discovery won the Nobel Prize and shattered our understanding of cosmic evolution. For decades, astronomers assumed that gravity would eventually win its battle against expansion. All that matter in reality should act like a cosmic brake, gradually slowing the expansion until everything either stops growing apart or begins collapsing back together. The team studying distant supernovae expected to measure this deceleration. Supernovae of a specific type called Type Ia explode with nearly identical brightness. This makes them perfect cosmic lighthouses. By comparing how bright they appear versus how bright they should be, astronomers can calculate precise distances to their host galactic formations. When they plotted these distances against redshift measurements, they found something impossible. Distant supernovae were fainter than expected. This meant they were farther away than the standard expansion model predicted. Somehow, Spatial dimensions had grown more than they should have during the light's journey to Earth. The only explanation was that expansion itself was accelerating. Something was pushing space apart with increasing strength. Researchers call this mysterious force dark energy, and it dominates everything. Dark energy comprises roughly 68% of the total mass energy content of reality. It outweighs all ordinary matter by more than 13 to 1. It outweighs even dark matter, the invisible scaffolding that holds galactic formations together. Yet we have no idea what it is. Here's what makes dark energy so bizarre. It doesn't clump or dilute. Normal matter becomes less dense as spatial dimensions expand. Spread a fixed amount of matter across twice as much space, and you get half the density. But dark energy maintains constant density even as space grows. As reality expands, new dark energy appears to fill the additional volume. This means dark energy's total influence grows over time. In the early cosmos, when everything was compressed together, matter and radiation dominated cosmic evolution, dark energy existed, but its sects were negligible compared to the gravitational pull of all that concentrated matter. As expansion spread matter thinner, dark energy's repulsive influence became more apparent. About 5 billion years ago, dark energy became the dominant force in cosmic evolution. This coincides roughly with when our solar system formed. Before that moment, expansion was slowing due to gravitational attraction. After that moment, expansion began accelerating due to dark energy's repulsive push. We live in the age of acceleration. Every day, dark energy becomes more influential. Every day, expansion accelerates slightly more. This acceleration is subtle over human timescales, but dramatic over cosmic time. In the far future, dark energy will dominate so completely that distant galactic formations will accelerate away from us faster than electromagnetic radiation can travel between them. They will disappear from our observable cosmos forever. But what exactly is this invisible force that controls the fate of everything? The leading candidate is vacuum energy moles, the quantum fluctuations that fill every point in spatial dimensions. Quantum field theory predicts that empty space should contain enormous amounts of energy. When researchers calculate how much energy the vacuum should have, they get an answer that's 10 to the power of 120 times larger than what we observe. This represents the worst prediction in the history of physics. Either our understanding of quantum mechanics is fundamentally flawed, or some unknown mechanism cancels out most of the vacuum energy, leaving just enough to drive cosmic acceleration. Alternative theories suggest dark energy might be a new field pervading spatial dimensions, similar to the electromagnetic field, but with different properties. Others propose modifications to gravity itself at cosmic scales. Some models envision dark energy as a dynamic field that changes over time, potentially leading to very different cosmic futures. The truth is, we're completely mystified by the force that controls our cosmic destiny. Dark energy could remain constant forever, gradually accelerating expansion until every distant galactic formation disappears beyond our horizon. Or it could decay, allowing gravity to reassert dominance and potentially reversing expansion entirely. It might even transform into something else entirely, fundamentally altering the nature of reality itself. We exist at the mercy of a force we cannot see, cannot touch, and cannot understand. We know as little about dark energy as ancient civilizations did about thunderstorms. This unknown force carves the future of the cosmos, causing space to accelerate outward. This acceleration began in earnest during a far more tumultuous era of growth. What unfolds when expansion itself outpaces light, in the first trillionth of a second after the birth of the cosmos? Space exploded outward with a ferocity that dwarfs every expansion in the nearly 14 billion years since. This phase, called cosmic inflation, stretched reality so violently that some regions permanently lost contact. Points once close enough to exchange signals were suddenly torn apart, separating them by unreachable distances. The cosmos shattered its own speed restrictions not by moving objects faster than light, but by stretching the very substrate of reality. During inflation, the stretch between any two spots doubled countless times each fleeting instant. Doubling happened faster than photons could bridge the growing gap. It's like two insects stranded on a rapidly inflating balloon, powerless to meet no matter their speed. Try to envision this: inflation grew the universe by a factor of at least 10 to the 26th power, a grain of sand becoming bigger than our entire observable reality. All this occurred in a period so brief, just 10 to the minus 35th seconds, that light could barely travel across a proton's width. That expansion was triggered by the infloton, a hypothetical quantum field saturating all of existence. Unlike typical quantum fields which rest at zero-energy ground states, the infloton lingered in a false vacuum, an artificially high-energy plateau. This created a temporary hypercharged version of dark energy, exponentially stronger than what propels cosmic growth today. While locked in this precarious state, the infloton pumped explosive power into every region of space, causing exponential growth. Exponential change creeps up at first, but erupts suddenly. Fold a sheet of paper 42 times, and its thickness equals the trip to the moon. Inflation brought this principle to the cosmos, with every infinitesimal instant doubling, redoubling, and multiplying the size of space-time itself. This rampaging growth answered monumental puzzles in physics: why the cosmic microwave background is nearly uniform across the sky, and why space appears perfectly flat. If the universe began with any curvature, inflation ironed it out to invisibility. Picture inflating a ball so much that it appears level from your limited viewpoint. Yet inflation's deepest effect is entwined with quantum mechanics. The expansion not only smoothed out the wrinkles in the fabric of space, it also magnified quantum jitters. Microscopic ripples present in the infloton's energies ballooned to colossal proportions. These tiny swells created the seeds from which galaxy clusters, stars, and eventually planets grew. Every structure, everything tangible, can be traced to randomness amplified billions of times during inflation. Your home galaxy, the sun that supports your planet, the molecules in your body, they all owe their existence to quantum strangeness, magnified in the earliest sliver of time. Each of us is part of a lineage descending from quantum foam itself. But inflation stirs an unsettling possibility. If these processes happened once, they could happen again. The same quantum fields that set off inflation in primordial times could still be present, waiting for the right trigger. A new episode could ignite anywhere, anytime, no warning, no sign. Such a bubble would expand at the speed of light, obliterating everything in its path and installing new laws, new physics, new realities. Even our atoms would evaporate, and the laws we rely on would evaporate with them. The appalling potential for sudden destruction isn't even the most mind-shattering implication. What if our universe is merely one swelling sphere among a teeming multitude of self-propagating realms? While you absorb these words, countless other universes may be burgeoning into reality, shaped by rules and constants utterly alien to our experience. This is not fantasy. It's a logical outcome of inflation theory. If inflation happens even intermittently, quantum randomness guarantees that it repeats, spawning fresh bubble universes across an expansive multiverse. Each burst of inflation births a cosmos which grows, matures, and cools, sometimes nurturing structures like galaxies and stars, perhaps even harboring atomic complexity and life. Our world is only one among an incomprehensible expanse of cosmic soap bubbles. What's most staggering? Every distinct bubble could operate under entirely different laws. Maybe gravity is far stronger, instantly converting stars to black holes. Maybe it's so weak that matter can never coalesce. Some universes might lack electrification, erasing chemistry altogether. Others perpetually inflate, never cooling, never allowing structure to happen. Most will be empty, sterile wastelands unfit for observers, inhospitable for atoms and energy to organize. Nonetheless, infinite bubbles mean that any configuration, no matter how improbable, arises somewhere. The specific balance of forces allowing life, as improbable as it may seem, will naturally occur infinitely across the multiverse. Our presence in a universe teeming with galaxies, stars, and chemistry isn't special. It's inevitable. Only in bubbles where observers evolve does the question of existence get asked, a simple truth known as the anthropic principle. The universe feels tailored for us not because we were intended, but because only worlds compatible with observation allow beings to wonder at their nature. Yet the concept of a multiverse brings its own philosophical paradox. If infinite worlds exist, Every conceivable event transpires somewhere. Each decision you forsake is enacted by another you, elsewhere. Every fork in reality is traversed by someone, in some bubble, an unending series of possibilities playing out forever. Every misfortune you've dodged finds a counterpart somewhere else, another you experiencing loss or heartbreak. Each dream that slipped away plays out for a different version, existing in some other world. The multiverse contains endless iterations of everyone, everywhere, living out every scenario. With infinite duplication, the whole idea of uniqueness evaporates. None of us stands alone if infinite copies are scattered through existence. Choices lose meaning. If every potential outcome is realized by some variant, our universe holds no special status beside infinite similar realms blinking into being alongside it. Still, the infinite multiverse remains untouchable. By its very nature, other bubble universes stay forever out of reach. Their light never touches us. Their gravity exerts no pull. Direct detection is impossible. We can't establish their presence or uncover what governs them. This philosophical dilemma frustrates scientists who believe untestable concepts cannot be science. Yet the equations of inflation point toward eternal expansion and ongoing creation of new universes. The same quantum math explaining our cosmic origins predicts perpetual bubble formation throughout the larger multiversal backdrop. Accept the theory, accept its wild offspring. Recent advances allow inflation's predictions to be scrutinized with growing accuracy. The cosmic microwave background, whispering faint patterns hidden in its static, echoes inflation's forecasted features. These results strengthen faith in inflation and, by extension, bolster the multiverse proposition. Paradoxically, we might live inside the best proof of infinite other realms. But this dizzying possibility presumes reality hosts only the three spatial dimensions we experience. Recent progress in theoretical physics hints at a much stranger scenario. Could expansion be happening along directions forever, outside human senses? The cosmos might be growing into realms that you can't perceive. The most ambitious attempt to unify all of physics, string theory, requires space to have 9 dimensions in total, far beyond the 3 that seem obvious. 6 additional spatial dimensions would be all around us, curled up tight so even subatomic particles cannot reach them. These hidden directions might expand too, just like the familiar ones. Imagine an ant exploring a garden hose. It travels forward or backward and believes space is one-dimensional. In truth, the hose has circular dimensions wrapped around it. The ant's size makes these too small to perceive. We may be just like that ant, aware of only 3 dimensions while others remain concealed beyond all experience. If such hidden dimensions exist, they might finally answer the question, what do cosmic expansions expand into? Our familiar 3-dimensional world could be growing inside the higher dimensional fabric containing it, much the way a balloon's surface swells through 3-dimensional space. Imagine our universe as a 3-dimensional brain floating in 9-dimensional hyperspace. All we know, all particles and forces but gravity would be stuck on this brain, while gravity escapes, leaking into the extra dimensions. This naturally explains why gravity's pull feels so feeble compared to the power of electromagnetism. The stretching we witness may be our brain expanding into hyperspace, but the thought becomes even more astounding. Other brains might exist beside ours, parallel yet almost impossibly close, perhaps separated by less than a hair's breadth along directions forever beyond reach. Another self could be reading these verses in the 4th spatial direction, fractions of a millimeter away, yet unreachable by every sense. On rare occasions, parallel brains might collide in these hidden dimensions, igniting what we perceive as a Big Bang. The cosmic microwave background radiation that we study today could be the aftermath of such a collision, jolting our brain and launching a new phase of cosmic evolution. Every few trillion years, these brains could crash again, spurring fresh bouts of creation. Mathematics tied to extra dimensions spins tales still stranger. Some models propose that these hidden parts of space are the ones expanding, while the 3 familiar directions remain unchanged. To us, expansion looks real, but it's actually the secret dimensions doing all the stretching. Imagine living on the outer surface of a balloon while its internal volume surges without our knowledge. Alternative theories suggest stretching and shrinking might happen at once. Visible space growing, hidden space shrinking. The total amount of real estate could stay the same, despite what appears to be cosmic growth from our perspective. These scenarios remain guesses. We can't probe extra dimensions directly. Even our most powerful machines, like the Large Hadron Collider, search in vain for particles sneaking off into hyperspace. So far, nothing's been found, hinting either at non-existence or dimensions far more tightly curled than theory predicts. Nonetheless, string theory's mathematics still calls for these extra directions, suggesting they are essential for the deepest unification of reality. If true, they would fundamentally rewrite what cosmic expansion means. The ultimate answer for what lies beyond could be simple. It expands into places you'll never see or sense. Even if extra dimensions aren't real, the shape of our common three-dimensional space might hold surprises. Perhaps space curves back on itself, converting the question into nonsense. The cosmos could be donut-shaped and expansion may simply make the donut's girth grow. While this raises eyebrows, geometry determines what cosmic stretching really means. General relativity allows for three classic shapes: flat space, like boundless graph paper, where parallel lines never meet, and the angles of a triangle always total 180 degrees. Spherical space, like the surface of a ball, where parallel lines eventually touch. If you measure the angles of a triangle in a closed universe, the total exceeds 180 degrees. This kind of geometry lets you travel straight ahead, never turning, only to end up at your starting point after circumnavigating the cosmos. Alternatively, space might curve like a saddle, where triangles have angles adding up to less than 180 degrees, and parallel lines drift apart. This open structure can stretch endlessly, but it bends away in every direction. Most evidence points to our universe being flat, though subtle curvature might exist at scales too immense to detect. Flatness doesn't guarantee infinity. A sheet of paper locally flat can be rolled into a tube, bent into a torus, or have edges joined to form a closed shape. The underlying geometry stays flat at small scales, but the overall shape is finite and loops back. If space wraps in this fashion, asking what our universe expands into is the wrong question. A donut growing doesn't fill external space, it simply fattens without invading anything new. This kind of topology would leave marks in the cosmos. If we lived in a donut-shaped universe, light could traverse the entire expanse and return to where it began, making it possible, in principle, to observe multiple images of the same distant galaxy appearing in different parts of the sky. Repeating patterns might show up in the cosmic microwave background, each one a ghost of light that circled reality multiple times. Astronomers have searched for such signs and so far found nothing. Either our world is staggeringly bigger than what we see, or it doesn't wrap at observable scales. Perhaps it is a donut so gigantic that not even ancient photons have completed one full trip around. The mystery grows deeper because space and time weave a singular four-dimensional tapestry. The universe's shape mixes 3 dimensions of distance with 1 dimension of duration. Expansion stretches not just where things are, but how time passes. Early on, when everything was packed dense, clocks ticked differently. Even the basic idea of now was alien. Simultaneity across far reaches didn't mean what you might expect. As the cosmos grows, it hauls time along for the ride. Space-time expansion isn't abstract. It's something we can measure. Distant galaxies race away at velocities that break ordinary comprehension, not because they're speeding through space, but because space itself undulates, taking them along. If you were a resident of one of those faraway realms, you'd see everything else retreating while you remained stationary, always witnessing yourself at the center of expansion. This relativity of movement means there's no privileged vantage, no cosmic headquarters, and no boundary advancing into an external region. The universe stretches by becoming more itself, not by infiltrating a void beyond. Resolving the paradox of expansion this way opens fresh enigmas, especially about time's nature and how its very flow might hinge upon the expansion of everything. How does the unceasing stretch of space impact the way time unfolds? Einstein taught that space and time merge in a unified space-time, stretch one, and you're inevitably stretching the other. When the universe expands, it tugs on the rhythm of time across the entire cosmic landscape. These effects ripple out, visible in real observations. Peer through a telescope at a remote galaxy, and it seems to drift outward. Now here's the mind-bending twist. Events in that galaxy play out in slow motion compared with nearby happenings. If a star suddenly explodes and takes 3 weeks to rise and fade close to home, that same process stretches far longer in some rapidly receding galaxy. Why? The light-carrying news of those events is itself stretched, not just in wavelength but in the intervals between bursts and flickers. This is literal time dilation. In spaces expanding quicker relative to us, time crawls. Light arriving from the edge of our observable world is redshifted about tenfold, meaning those galaxies were sprinting away at nearly 90% the speed of light when they produced that light. Events there appear to pass 10 times slower than locally. This breeds the surprising result that the universe's age depends on where you are. From our vantage point, reality is about 13.8 billion years old. But from those swift, distant galaxies, our zone seems much younger. The fabric of cosmic time has been stretched out. Your experience of the age and passage of time is not universal, but location-dependent. This temporal stretching reveals essential truths about cosmic evolution. The infancy of the universe didn't just hold compressed matter, it harbored compressed time. Things that take eons in the present unfolded much faster upon that denser stage. The rise of the earliest stars, the birth of the first galactic swarms, and the formation of primordial black holes all happened in a universe where temporal tick rate differed dramatically from modern norms. But expansion tinkers even more deeply, altering the notion of simultaneity itself. What seems self-evident day to day, that events happening together are simultaneous everywhere, is an illusion on the cosmic scale. Relativity and the steady stretching of space-time mean that now ceases to be a universal concept. Two distant observers might disagree entirely about whether things happen together or at separate times. There's no single cosmic present. Every region hosts its own slice of now, disconnected from others by distance, velocity, and the relentless march of expansion. As the stretching of reality accelerates, these effects intensify. Cosmic time evolves and simultaneity shatters, painting a far stranger portrait of existence than common experience would ever suggest. With every passing era, dark energy's dominance intensifies, pushing the expansion ever faster and further, stretching not only the distances between galaxies, but the very flow of time itself. As this acceleration continues, future civilizations peering out from our galaxy will witness even more dramatic time distortion. Their telescopes will reveal distant realms moving so quickly that reality appears frozen in distant locales. Cosmic expansion's pace will eventually slow time to a crawl. Faraway events all but stop. Such radical acceleration leads to a chilling question: what is the ultimate outcome when expansion supersedes every fundamental force? Our universe speeds toward a future so barren and cold that no spark of energy or organized process survives. This inevitable terminus, cosmic heat death, marks the point where expansion triumphs over everything else. Space will continue stretching until matter and energy are dispersed so thin that only an empty dark void remains, its temperature hovering just above absolute zero. The schedule for this conclusion is almost beyond imagination. After around 100 billion years, the final stars will burn out, their fuel spent sinking into darkness. Gravity will lack the means to pull material together for new stars. The dwindling supply of matter cannot clump and ignite anew. The universe will enter its degenerate era, dominated solely by the cold, fading relics of once brilliant stars, stellar corpses scattered through growing emptiness. Yet that's not even the whole story. After a span lasting an estimated 10 circumflex 34 years, even the protons composing your body, planets, and all familiar material will spontaneously disintegrate, breaking into lighter particles. Atoms themselves will cease to be. Scattered through the growing void will be only electrons, positrons, and stray photons, the last echoes of the matter that once filled everything. These numbers dwarf all scales we can grasp. If the universe's present age were a single second, the proton decay epoch would persist for more than a billion years. And still, this extraordinary stretch of time is minuscule compared to what comes next. Once 10 circumflex 100 years have gone by, black holes will remain as the universe's only noteworthy engines. Even these will slowly dissolve through Hawking radiation, transforming their mass into energy so slowly that stellar mass black holes require lifespans exceeding the universe's current age. The titans at galactic centers, the supermassive black holes, persist for 10 circumflex 100 years before finally vanishing. When the final black hole evaporates, the universe will reach perfect equilibrium, absolute entropy, where no heat, no light, no difference endures. Chemistry ends, computation halts, life becomes impossible. The cosmos grows utterly uniform, a place where the march of entropy has leveled everything. Unless some mechanism alters dark energy's course, this frigid, silent future will arrive. Expansion will continue, matter and energy thinning into nothingness. As space stretches ever quicker, galaxies outside our local group will slip away, becoming invisible as their light can never bridge the ever-growing gap. Though not destroyed, they fade so far into the distance that all evidence of their existence vanishes. In about 150 billion years, only the handful of galaxies in our immediate group will remain visible. Future astronomers will see a universe that seems to contain just a few faint smudges surrounded by an endless blackness. All signs of cosmic expansion disappear beyond our horizon. Star watchers in future centuries nestled inside the Milky Way may believe they inhabit a small, static universe. The cosmic microwave background, our most direct proof of the Big Bang, will become so redshifted by expansion that it's undetectable. Civilizations emerging in these epochs will lose the historical clues that let us grasp cosmic origins. They'll perceive reality completely differently, perhaps never learning of the universe's vast past. Even this narrowing of cosmic perspective is trivial compared to a more devastating scenario. If dark energy continues intensifying, expansion might eventually overwhelm forces holding matter together, erasing gravity, upending electromagnetic bonds, even shattering the nuclear forces holding protons and neutrons. The universe might not merely empty out, but shatter molecular structure at every scale, tearing reality apart. Before confronting this catastrophic speculation, we must understand what nothingness actually means, what really fills the empty spaces between and inside everything. The void is not empty. Instead, it's a seething cauldron whose violence rivals the core of the sun. At reality's tiniest scale, space boils with virtual particles flickering in and out of existence, their lifespans so brief that ordinary detectors cannot catch them. Zoom into what seems empty with a microscope powerful enough to peer far below an atom's nucleus, and at the Planck scale roughly 10 circumflex 35 meters, the fabric of space turns turbulent and crumbly, wavering and roiling, chaos replacing smoothness. Here, virtual particles borrow energy briefly. Thanks to Heisenberg's uncertainty principle, the more they borrow, the faster they repay by colliding and vanishing. Though this cycle unfolds too swiftly for conventional observation, it abides perfectly by quantum law. The vacuum is alive with surging energy and activity. Electron-positron pairs burst into existence for a fleeting 10 circumflex 21 seconds before annihilating. Heavier, briefer pairs flicker yet faster. Every type of virtual particle permitted pops in and out inside what seems completely empty. These fluctuations carry tangible effects. Laboratories have measured forces generated by quantum foam. The Casimir effect, for example, happens when two metal plates are placed very close together in a vacuum. Only virtual particles with wavelengths small enough to fit between the plates can exist, while longer wavelengths can only persist outside. The resulting imbalance nudges the plates together, generating a measurable push. The quantum vacuum literally exerts pressure, a subtle force produced by the invisible dance of virtual particles. But here sits why quantum foam truly matters cosmologically. All those ghostly virtual particles, flashing in and out of nothing, should add up to an enormous energy density in every cubic centimeter of vacuum. When physicists crunch the numbers, summing every quantum fluctuation allowed, they get an answer so large it would cause the cosmos to balloon at rates utterly unlike anything we witness. A full accounting of quantum foam predicts vacuum energy levels up to 10 circumflex 120 times greater than the measured value of dark energy. A calculation so wildly off base, it stands as theoretical physics' greatest embarrassment. Either something fundamental in our quantum models is deeply mistaken, or the universe deftly cancels out most vacuum energy with some unknown process. Solving this vacuum catastrophe may hold the key to understanding dark energy itself. Maybe there's a mysterious balancing act. The bulk of quantum energy suppresses itself, leaving behind just enough to fuel gentle cosmic acceleration. Perhaps only a tiny remnant of quantum foam survives, pushing the universe to stretch ever quicker. Or maybe we're altogether wrong. Our models, our equations, our concepts for vacuum energy built upon incomplete knowledge. Some alternatives propose empty spaces unlike anything we imagine. Perhaps hidden fields saturate the vacuum, or energy sneaks into extra dimensions beyond what we perceive. The illusion of pure emptiness might mask layers of activity, space itself a built structure with intricate components. If space is truly made of something, expansion could simply mean stretching those constituents, not creating new emptiness at all. Loop quantum gravity sees space as countless tiny units linked together, a geometric crystal weaving reality. String theory places vibrating filaments within extra dimensions at the heart of existence, with space forming from their complex entanglements. In these views, empty space is filled with internal parts, and expansion stretches what already exists rather than adding true void. The cosmos wouldn't swell into nothing. Space itself is a thing, just not one we understand yet. But our uncertainty about emptiness and quantum foam is mild compared to the fate that might await if dark energy's power keeps climbing. If the vacuum grows more unruly, what evolves when expansion outpaces every restraining force? In about 22 billion years, increasing dark energy could rip apart every atom, reducing reality to its most basic elements, a process called the Big Rip. Compared to heat death's slow dimming, the Big Rip is an abrupt, violent destruction. Imagine the timeline. About 1 billion years prior, dark energy would break gravity's bind on galactic clusters, letting each galaxy drift away into true isolation. Roughly 200 million years before the climax, even individual galaxies come unglued, stars tear loose from their galactic homes, the Milky Way breaks up, Andromeda disintegrates. Every collection of stars dissolves into lonely wanderers, fending off the growing expanse. 30 minutes before the end, the pulling force of expansion overtakes the gravity-holding solar systems together. Planets, moons, and stars all part ways. Earth escapes from the sun. The moon vanishes into darkness as well. In the last moments, expansion overtakes molecular bonds, atmospheres scatter. Oceans boil away as space stretches faster than intermolecular forces can preserve cohesion. Just before the Big Rip, the universe's violence outpaces nuclear glue, and atomic nuclei split apart. The matter forming worlds, stars, and life reverts to protons and neutrons, scattered helplessly. At the precise instant of rupture, even space and time may come undone, as the metric for measuring intervals, distance, time breaks down. Causality fails. Reality dissolves into nonsense. It's not just an ending, it's the disappearance of existence itself. Of course, this nightmare only plays out if dark energy's behavior changes, if its strength ramps up. If the vacuum remains stable, our universe will instead drift toward heat death, fading quietly. Observations so far show dark energy holding steady across history, but subtle shifts cannot yet be excluded. Future measurements tracking distant stellar explosions and cosmic landmarks could pinpoint changes in dark energy's power. If it is accelerating, we can forecast the moment of total unraveling with unsettling precision. Conservative numbers put the Big Rip about 22 billion years ahead. Some calculations say it could occur much sooner. No matter the schedule, such outcomes challenge our long-term optimism. But even cosmic collapse might seed rebirth. Some theories predict that the Big Rip's violence could kick off new inflation, spawning fresh bubble universes from the fragments of the old. Perhaps reality is always recycling, tearing itself apart, only to build again. Before fully grasping any of these ends, we must examine how the stretching of everything is measured. The tale of cosmic expansion began not in the realm of equations, but through the lens of observation. How do astronomers measure the growth of something as vast as space itself? The process uses exploding stars, stellar death flashes, as cosmic measuring sticks, mapping how far the universe has stretched. This is no simple feat. Measuring distance to far-off objects billions of light-years away requires extraordinary ingenuity. Observers must discern whether these objects are racing away due to intrinsic movement, or because the space between points grows ever larger. The solution is found in the consistent violence of dying stars. Type Ia supernovae explode when white dwarfs soak up too much matter from their companion stars, releasing a burst that always shines with nearly identical intensity. These cosmic explosions scatter the same amount of energy wherever they happen, turning them into perfect standard candles for measuring distance across the universe. Here's how astronomers use these explosions to take the universe's measure. When a Type Ia supernova occurs in a nearby galaxy, its observed brightness is compared to the known intrinsic brightness calculated from physics. The difference reveals exactly how far the outburst happened, since more distant objects appear dimmer. At the same time, astronomers analyze the red shift from the light, the degree to which its wavelengths have been stretched on the journey through the inflating cosmos. Larger redshift means the light has crossed more expanding space, pointing to greater distances and earlier epochs in cosmic time. By plotting the measured distances against red shifts for hundreds of these explosions, a map of the universe's expansion history emerges. If expansion was steady, the results would draw a straight line. If gravity was slowing expansion, distant supernovae would be closer than expected. If expansion were accelerating, these supernovae would seem farther fainter than the model predicts. The data shows exactly this acceleration is real. Ancient supernovae shine less than they would if the cosmos grew at a fixed rate, revealing that expansion has outpaced expectations. Cosmic stretching has accelerated under the influence of dark energy for billions of years. And astronomers don't rely on only one approach. They build a structured system called the cosmic distance ladder, calibrating each rung with the one below. The bottom tier uses parallax, measuring how nearby stars shift against background stars as Earth orbits the Sun, allowing careful triangulation out to hundreds of light-years. These carefully gauged distances are then used to calibrate the next rung, Cepheid variable stars. Cepheids pulse in a rhythm directly linked to their true brightness. By timing these pulses and noting apparent brightness, astronomers deduce the distance. These variables are visible in galaxies up to 100 million light-years away. Cepheid-based distances then calibrate supernovae, extending the reach to billions of light-years. Each step depends critically on those beneath, making the whole system vulnerable to errors that could ripple up the ladder, leading to one of modern astronomy's greatest puzzles. Different measurement techniques yield slightly differing values for the Hubble constant, the number expressing cosmic expansion rate. Local distance ladder methods yield about 73 kilometers per second per megaparsec, while cosmic microwave background analyses point to a lower value, closer to 67 kilometers per second per megaparsec. This 6% difference might sound small, but in cosmology it's a crisis. Either unknown errors are lurking in our methods or our theories miss something fundamental. Solving this Hubble tension might require new physics or finding systematic mistakes that have eluded careful observers. Yet amid the debate, both measurement systems align on the fundamental truth: the universe expands and that expansion is speeding up. But how do scientists turn these observations into precise descriptions of cosmic evolution? They rely on a mathematical tool called the scale factor, often denoted by the letter A. This simple variable captures the swelling of space over time, translating cosmic events into mathematical clarity. When the scale factor doubles, every distance in the universe doubles with it. When it triples, all distances triple. By tradition, cosmologists set the present scale factor to 1, marking earlier cosmic times by values less than 1. In the future, as space stretches, the scale factor will rise above 1, a direct intuitive way to track the universe's expansion through past, present, and future. This framework allows precise connections between observed phenomena and cosmic eras. When you observe a galaxy showing a redshift Z, you're peering back to a time when the scale factor was 1/1 plus Z. A galaxy with redshift of 1 existed when the universe was half its present size. Radiation from the cosmic microwave background, with a redshift near 1090, was emitted when the scale factor was just 0.001, meaning space was only 1,000th its current stretch in each direction, and the volume a billion times smaller. But the scale factor does more than describe what happened. Combined with Einstein's field equations, it predicts tomorrow's cosmic stretch. The fate of expansion depends on how the scale factor changes over time. Linear growth means constant expansion. If it climbs faster than linearly, expansion is accelerating. Slower growth signals deceleration. Observations show that expansion has accelerated for around 5 billion years. The mathematics point to 3 possible futures, all hinging on dark energy's behavior. If dark energy remains steady, the scale factor inflates exponentially forever, leading to heat death as matter is spread thin. If dark energy strengthens, the scale factor surges even faster, ushering in the Big Rip. If dark energy wanes, the scale factor slows and the universe could collapse in a big crunch. Current data overwhelmingly favors everlasting acceleration, but the power of the scale factor extends deeper, illuminating profound truths about expansion itself. How rapidly the universe stretches at any moment traces directly to its total energy density. All the contents, matter, radiation, dark energy, set the expansion's pace. In the cosmos' infancy, space squeezed all contents into a tiny volume, energy density soared, and the universe billowed out at breakneck speed. As space expanded, energy spread thinner, slowing the outward rush. But around 5 billion years ago, dark energy's steady strength began dominating, shifting cosmic expansion back into acceleration. The scale factor, marching through cosmic history, captures all these transitions: slow starts, sudden speed, and what lies ahead. By blending theory with observation, cosmologists calculate the quantities of each cosmic ingredient. Today's universe is roughly 68% dark energy, 27% dark matter, the invisible skeleton holding galaxies together, and only about 5% ordinary atoms, the stuff we see, touch, and use. The scale factor predicts that, as reality stretches, matter will grow ever more dilute while dark energy silently maintains its steady density. Eventually, dark energy will reign, driving exponential swelling in every direction. Yet the mathematics underlying cosmic expansion build upon astonishing twists, and what might be history's greatest scientific misstep. Once upon a time, even the sharpest minds believed the universe stood motionless, unchanging and eternal. When Einstein finished his theory of general relativity in 1917, it dictated that the cosmos should either expand or collapse, never holding perfectly still. But astronomers of the day trusted observations and rejected a dynamic universe. The notion that all of existence could be growing or shrinking sounded absurd. Puzzled, Einstein tweaked his equations, appending a term, the cosmological constant, lambda, intended to provide a gentle repulsive push, balancing gravity and keeping space static. This constant represented the energy of the empty void, an inherent property of space offering just enough outward pressure to halt gravitational collapse and stabilize everything. For years, it seemed a clever solution. Then observations changed everything. Edwin Hubble's careful measurements revealed that distant galaxies are all racing away, that the universe is not static but stubbornly expanding. Einstein, stunned by the real data, repudiated his constant, calling it his greatest blunder. Had he trusted his original mathematics, he would have predicted expansion well before the evidence appeared. Instead, he spent years trying to erase the term, a twist that would echo through the decades. In 1998, the cosmos offered another surprise. Observers discovered that expansion was not just real, but gaining speed. An unknown force was driving space outward, just as Einstein's cosmological constant had been meant to do. Today, the best-fitting models use a subtle, uniform energy density filling every nook of space, precisely what Einstein's lambda described. Modern cosmology relies on this term to explain dark energy's effects. If the answer is correct, then Einstein's intuition about vacuum energy, despite being a genuine blunder, was heartbreakingly accurate. The value of lambda may be tiny, but multiplied by the universe's vastness, it supplies more energy than all ordinary matter and radiation combined. What was once considered unnecessary now steers cosmic fate. Yet this success comes paired with a new conundrum. Vacuum energy drives acceleration, but theory indicates it should be enormously larger. 10 circumflex 120 times more, according to quantum field estimates. This gulf between theory and reality is physics' most glaring unresolved mystery. Either we misunderstand quantum mechanics at its core, or the universe employs unknown mechanisms to cancel almost all vacuum energy, saving only a sliver for cosmic expansion. Solving the puzzle may demand whole new branches of science. Some propose dark energy might not be a statutory constant, but a dynamical field that shifts and evolves. These ideas could skirt the vacuum catastrophe while explaining cosmic acceleration. Still, observations best match a steady, omnipresent energy, perhaps validating Einstein's original guess after all. The irony echoes back through the ages. Einstein added lambda to freeze the universe in stasis, erased it when expansion was unveiled, and now cosmologists restore it to explain why space races apart faster every day. The most famous blunder may have become the most prescient calculation. Yet even this tale, built upon bold theory, draws strength from the adventure of looking outward. Imagine an astronomer aiming a telescope skyward, only to find everything assumed about the universe utterly wrong. Edwin Hubble spent countless nights in 1929 peering into the ghostly spiral nebulae with the world's largest mirror. He debated with colleagues, were these odd patches merely clouds inside our own galaxy, or star cities positioned far beyond? His results settled the argument. They were distant galaxies, and that wasn't the true revolution. When Edwin Hubble pointed his telescope at the misty spiral nebulae and used Cepheid variable stars as markers, he measured distances that placed these clouds millions of light-years away, far beyond the Milky Way's limits. Overnight, the cosmos grew from a single galaxy to a collection containing countless others, each billions of suns strong. But as Hubble charted galaxy distance against velocity, a pattern emerged, impossible yet undeniable. Every galaxy he could measure was fleeing, its starlight stretched to longer, redder wavelengths. Not just some galaxies, not only the distant ones, each and every galaxy drifted away from the Milky Way. At first glance, this seemed to thrust our planet into a privileged spot, Earth at the center of some tremendous explosion. Stranger still, the farther each galaxy, the faster its retreat. Double the distance, double the velocity. Triple the distance, triple the speed. Today, this proportionality is known as Hubble's law. Recessional velocity is directly tied to distance. Hubble himself initially thought galaxies might be physically moving away into static emptiness, debris sailing from a cosmic blast, but that didn't add up. If every galaxy fled from us, why were we special? The Copernican principle insists Earth doesn't occupy a unique place. The answer revealed a more profound truth. Space itself was stretching, carrying galaxies with it. Picture a balloon inflating. Dots on its surface recede from each other as the skin stretches, yet none are special, none at the center. Each dot would see the identical pattern Hubble measured. Thus, Hubble's discovery marked the transition from thinking about motion through space to realizing that the fabric of space expands, moving everything apart as if galaxies are raisins caught in rising dough. The slope of Hubble's law, the Hubble constant, captures how quickly space grows. If the constant is high, expansion races. If low, growth slows. Hubble's original value was much too high, predicting a universe younger than Earth. He'd confused two types of variable stars, underestimating distances, but later astronomers fixed those errors. The age of our universe comfortably overtook that of our planet, but the essential relationship Hubble found remains robust. Across distances from local galaxies to the farthest observable, the universe expands according to Hubble's law, proof that expansion is a trait not of isolated regions, but of space itself. This breakthrough gave astronomers a true distance scale, transforming the field from a two-dimensional mapping of sky positions to a three-dimensional cosmic cartography. Suddenly, humanity's home was revealed as a minuscule part of a dynamic, evolving, expanding universe, one that began dense and hot and as cooled as it spreads out through time. Yet Hubble's law posed a bigger question. Would expansion last forever, or would gravity halt it and trigger a collapse, an eventual big crunch? The outcome depends on how much matter actually exists, how much stuff is present to slow infinity's growth. There's a precise tipping point called the critical density that determines cosmic destiny. It works out to about 5 hydrogen atoms per cubic meter, scarcely anything compared to the vast emptiness of space. But even this wisp of matter decides whether the universe expands eternally or someday reverses course. The physics behind critical density arises from a battle between expansion and gravity. Expansion drags everything apart, spreading galaxies thinner and farther every moment. Gravity acts in opposition, attempting to draw matter together to halt and perhaps reverse this spread. If cosmic matter density tops the critical value, gravity wins. Expansion stalls, halts, and ultimately reverses into a fiery collapse. If there's less matter, expansion wins. The universe grows forever, approaching heat death as matter is whisked away into infinity. If total matter hits exactly the critical density, expansion slows gradually, approaching zero but never quite stopping, perfect balance, like tossing a ball upward with exactly the speed needed to fade away, forever slowing but never falling back. For decades, measuring the true amount of matter was cosmology's greatest challenge. Just count the stuff and divide by the space, it seems simple. But reality proved far more subtle. Most matter in the universe is invisible. Galaxy rotation curves revealed that stars in outer arms orbited faster than visible mass could explain. These observations demanded much more unseen gravitational heft than luminous stars showed. Thus, dark matter was born, matter that doesn't emit, absorb, or reflect light, but which shapes galaxy motion through its gravitational grip. Despite being undetectable to telescopes, dark matter outweighs visible matter by more than 5 to 1. When scientists tallied up both ordinary and dark matter, the total density reached only about 30% of the critical value, a universe poised to expand forever towards silent entropy. Then, everything changed with the discovery of dark energy. The balance between fading into meaningless expanse, collapsing into fiery rebirth, or coasting in perfect equilibrium now shifted again. Dark energy doesn't set, just contribute to cosmic energy density. Dark energy doesn't just add to the universe's tally, it fundamentally transforms how expansion works. Unlike gravity's draw, dark energy exerts a cosmic push. In Einstein's equations, any form of energy density mixed with strong negative pressure causes space to stretch faster and faster, accelerating expansion beyond anything gravity can slow. This throws the classic notion of critical density into a new light. It assumes matter and energy only pull, but dark energy's repulsion makes continued acceleration inevitable, no matter how much ordinary stuff exists. Current observations put our universe at about 27% dark matter, 68% dark energy, and 5% regular matter. Numbers that bring us uncannily close to the textbook definition of critical density, but only after factoring in the strange effects of negative pressure. That razor's edge is no accident. In fact, it creates a major riddle for cosmology, the so-called flatness problem. Why should cosmos be perched so precisely at the tipping point between endless expansion and eventual collapse? In most cosmic models, density rockets far above critical, causing quick collapse, or plummets well below, sending matter scattering into empty infinity. Maintaining a near-critical density requires initial conditions to be fine-tuned to an astonishing degree. Cosmic inflation supplies an elegant solution. During a flash of exponential growth, any initial cosmic curve is ironed out to near flatness, and the universe emerges balanced. That's likely why we see such critical density today, because inflation flattened everything long ago. Yet the alignment feels oddly coincidental. We live right when matter, dark energy, and dark matter have similar bearings on cosmic destiny. Just a blink ago, matter shaped expansion in a few billion years. Dark energy will take over completely. We exist amidst this fleeting transition where all the ingredients count. It's tempting to think it's mere selection bias. Only in epochs near critical density can observers arise and question their origins. In chaotic, violent beginnings, nothing complex survives. In barren futures, growth ceases. Perhaps only near-critical universes brew minds capable of pondering their own existence. But even this logic assumes our cosmos is alone, one universe racing outward from one big bang. What if expansion rages in countless realities, each with its own destiny? Right now, while you absorb these words, trillions of other universes may be inflating, each stretching from a unique birth across directions you cannot picture. These parallel realms wouldn't lurk somewhere far off in our own cosmic space. They would exist in totally distinct arenas, each with its own spatial and temporal dimensions, its own expansion story. In additional inflation, our visible universe is but a patch of a vastly larger realm. Inflation never halts. Quantum randomness triggers new cosmic outbursts across the expanse, birthing bubble universes that expand and evolve independent of each other. Each bubble carves its own laws, constants, and storylines. Some stretch for trillions of years, others for mere moments. Some expand at breakneck speed, driven by furious dark energy, others amble slowly, packed with more matter. There are bubbles doomed to quick collapse, entire histories flickering in and out in a cosmic blink. Elsewhere, universes rush toward violent rips, annihilating themselves in a final spasm. The multiverse vision grows even stranger. Some theories propose that every quantum measurement splits reality, each outcome forges a fresh universe, branching infinitely. Every possibility unfolds somewhere. Most will mirror our own, diverging by only quantum hairbreadths. Others branch wildly, reshaped by tumultuous events. Some domains see dark energy dominate, fueling runaway expansion. In others, gravity snuffs it out and everything falls back together. In this quantum landscape, parallel selves experience every fate: heat, death, violent rips, sudden collapses. Expansion plays out across infinite tapestries, and every story occurs. That leads to a haunting realization. Does our particular history matter if infinite variations unfurl simultaneously? Some say the multiverse renders individual outcomes meaningless, making destiny irrelevant. Others argue each universe matters desperately to its inhabitants, unique against an infinite backdrop. The idea also complicates our grasp of expansion itself. In a single cosmos, growth stretches all space. But in a multiverse, expansion might be only one layer of a more massive structure. Our universe could inflate while the broader multiverse remains static, or the whole multiverse could be growing in ways that go beyond space and time as we know them. Scientists have started searching for faint hints of parallel universes, scanning the cosmic microwave background for subtle signs of cosmic collisions. So far, the sky remains quiet, but missing evidence is not the same as proof of absence. Perhaps the scales and subtleties are simply beyond our reach, leaving us forever pondering the reality of parallel expansions. Even if parallel universes stay invisible, our own expansion brings deep questions about meaning and persistence. As space races outward toward infinity, what happens to all information, your thoughts, memories, and identity, that lives as tangible arrangements in matter and energy? Cosmic expansion pulls apart the intricately woven patterns that hold memories, identities, and meaning. This slow stretching creates a paradox at the heart of physics. Information is said to be indestructible, yet expansion scatters it so far that it vanishes from practical reach. This conundrum springs from the holographic principle, the mind-bending idea that information contained within any region can be encoded on the surface bounding that volume. Imagine the universe as a giant hologram, storing three-dimensional data on two-dimensional boundaries. As expansion increases the universe's surface area, the total information that can be written grows, letting new patterns and complexities arise, even while the old ones dissipate. Our own minds are built on arrangements, networks of neurons, molecules, and atoms, all fixed in place by the geometry of space. As the universe stretches, those arrangements drift apart faster than any force can keep them together. Over eons, the atomic configurations making up a thought would eventually be separated by cosmic distances, disintegrating the information that once defined consciousness and individuality. Identity dissolves into space-time's outward march. Yet quantum mechanics refuses such neat conclusions. Quantum entanglement lets particles remain linked over immeasurable distances, defying the isolation wrought by expansion. Correlated quantum states might persist independent of physical separation, hinting that some kinds of information could survive, even as matter itself wafts apart. Expansion, however, mounts another challenge: the loss of causal connection. As space grows, once communicating regions speed away until light itself is too slow to bridge the gulf. These regions become causally locked, trapped in their own isolated cosmic bubbles. Whatever happens within can no longer affect, or be affected by, anything outside. The observable universe's information, once unified, becomes fragmented. This growing isolation may seem to break the rules of quantum theory, which holds that total information can never truly vanish. But resolution may arise from realizing that information operates on multiple scales. While local patterns vanish into distance, cosmological patterns may emerge larger than before. The story of expansion itself, encoded in cosmic microwave background, the map of galaxies, the arrangement of space-time, incorporates its own memory, information that persists on vast scales, even as details evaporate. Yet even this cosmological information eventually faces oblivion. As expansion accelerates, the cosmic microwave background is stretched beyond detection, its wavelength longer than the observable universe itself. Future astronomers will lose touch with all traces of a hot, dense birth. Civilizations emerging in this far future will find no clues to cosmic origins. They'll conclude the cosmos is small, stagnant, forever the same. The journey from teeming galaxies racing apart to a lonely island adrift in emptiness will remain undiscovered and unimagined. This fading of cosmic perspective strips even more than history. Without evidence of ancient light or racing galaxies, tomorrow's universe also loses access to the physics that shaped the beginning. The redshift relationship central to Hubble's law becomes invisible. No distant galaxies, no expanding space, no clues in the sky for the scientists who follow. They may guess at different causes, create alternate cosmologies, or truthfully believe their isolated galaxy has floated unchanged forever in limitless void. The evaporation of cosmic memory underscores a profound truth. Information is temporary, meaning is fleeting. The patterns that define civilizations, consciousness, and even cosmic structure survive only as long as the universe continues, offering a stage on which they can dance. Perhaps it's the brief shimmer, the momentary pattern, that brings significance, not immortal preservation, but spectacular existence in a fleeting window. Yet when expansion ultimately eliminates all observers, even these philosophical comforts may vanish. As the cosmos ages, 150 billion years from now, the sky will tell a story so different from today's dazzling tapestry of galaxies that no one could ever guess its true history. Meaning, knowledge, and even wonder fade along with the starlight that once filled the night, leaving only a silent, solitary galaxy adrift in infinite space. Cosmic nuclear forges that blended the first elements completed their labors billions of years ago, leaving behind only subtle traces in the ancient chemistry of stars. In distant epochs, future civilizations will search for answers in a universe almost silent, filled with clues that have faded far beyond the reach of their instruments. With intelligence and technology equal to ours, they'll peer into the void and find a reality that withholds its most important secrets. Their scientific methods will reveal much, but not the cosmic truth. The universe they observe will deceive them. It's impossible to escape the haunting question: might we be equally blinded by our position in time? Are there cosmic revelations, fleeting and magnificent, that slipped away before our arrival? Perhaps beings forming just after the Big Bang saw wonders forever hidden from us. As cosmic expansion transforms the universe, even the life-sustaining processes we rely on will disappear. Star birth will end when gas grows too thin for gravity to trigger collapse. Brilliant stars will burn their last, fading into cold embers. Black holes will vanish slowly, evaporating until nothing but scattered elementary particles remain adrift in emptiness. Heat death looms. The universe will become nearly featureless, and any conscious survivors will see an even more cryptic cosmos, one that erases memory and history so thoroughly that only the present remains. All this springs from a deceptively simple query about cosmic destiny. Where does the universe expand to? Does expansion have a target, a destination, a reason? Expansion may not travel toward any goal at all. It may be its own justification, a process defined by the fleeting complexity it creates, not by some fixed outcome. Everything we see, from galaxies and planets to life itself, arises because expansion crafts the active stage on which cosmic drama unfolds. Without growth, reality would stagnate or collapse, never developing the intricate beauty we marvel at every day. Expansion manufactures not only the space and time we live in, but also the very framework for meaning itself. Asking where it expands is like searching for the outside of existence, or wondering what lies beyond the edges of logic and language, a question that collapses under scrutiny because expansion defines and creates what outside and into mean. There is no arena waiting to be filled. When the universe expands, it doesn't invade anything. It creates the notion of anything. This isn't a limitation of words or imagination. It's a feature of reality. Before expansion, concepts like inter and beyond have no meaning. Expansion isn't simply the stretching of space. It's the birth of the entire logic by which we define relationships. The universe expands into itself, growing the parameters for possibility with every moment. Think of it as the ultimate cosmic bootstrap. Asking what the universe expands into is like questioning what holds the container holding all things, or what caused the first cause. The categories you invoke only come into play after the thing you're asking about exists. The universe doesn't expand toward an external goal. It becomes more universe, enriching its own tapestry and inventing new possibilities. The real miracle of expansion is not mechanical, it is existential. With each pulse of new space, reality offers fresh flooring for experience, matter, complexity, and even the emergence of consciousness. We're not drifting along on a cosmic journey to an unknown edge. We are part of the very process by which reality assembles itself from nothing but possibility. Our awareness, our relentless searching, our burning need to unravel expansion's mystery, these are not separate from the universe's expansion. They are expressions of it, woven deeply into the story. We are expansion. We are space, time, energy, and pattern, organizing themselves just enough to become conscious, to ask and wonder at their own existence. This perspective not only answers the paradox of cosmic expansion, it opens a deeper doorway. If reality creates its own dimensions, if it serves as its own stage and observer, what we call existence could be stranger than any story dreamed up in fiction. We might be living within a self-creating process, one that has no outside, no endpoint, and no reason, save the breathtaking truth of its own unfolding. The universe expands into itself, endlessly, giving rise to infinite opportunities, including the birth of beings able to love, question, and rejoice in their place within the grand experiment. The original question, what does the universe expand into, leads through inflation, through the push and pull of mysterious energy, through the endless branching of multiverses and the subtle dance of quantum foam. It takes us toward the beginning and end of time itself. Yet, the deepest answer was always hiding in every moment of wonder and curiosity. The universe expands into mystery, into anticipation, into the infinite capacity for new possibility. Through every unfolding discovery and question, through every awestruck reflection, we find ourselves woven into something greater, a living universe, asking itself where it's going and awakening to its spectacular self-invention. We are reality becoming aware. We are the question, the journey, the answer, and the celebration of the impossible glory of being here now, as the universe expands endlessly into wonder.